Thank you very much, Markl. So my name is Yasmin Markl. My colleague is Andreas Wirth. We are both working for the Austrian National Weather Service, ZAMG. Hello from home office today. And I would like to start this weather briefing with an overview about the current weather situation in Europe. And Andreas will then do the second part with a surprise topic. So, as you can see, this animation is a water vapor satellite image animation since January, and I would like to focus a little bit on the water vapor images in the next couple of minutes. As I have said, this is since January, so it's very quick, but you can already see the complexity. It's almost like milk in a cup of coffee or tea. And I'm wondering, am I the only one feeling that this is different from what you see when you look at the sky? So if you look at the sky, you might expect somehow different weather than this kind of coffee-milk mixture. This water vapor image is indeed a very powerful tool, so I would like now to say a little bit about it. Water vapor is a trace gas that tells about the origin and the kinematics of an air mass. Let's start it again. In this respect, water vapor images can reveal features that other channels, like infrared channels or visible satellite channels, images are not capable of showing. And I will start with a little theoretical background. Maybe it's a small reminder for some of you. Satellites receive the radiation from Earth in different wavelengths. And some of the wavelengths, some go through a window, so to speak, directly to the satellite. We see some, for example, here in the visible area. And some are absorbed by, for example, a gas and re-radiate to the satellite. Those are the so-called absorption channels, as we have, for example, here in the water vapor absorption. And two of them, channel 5 and channel 6, are in the range between 5.2 and 8.5 micrometers and are the so-called water vapor absorption channels. The radiation in these channels represent the temperature and amount of water vapor in the middle and upper troposphere. So why in the middle and upper levels? The radiation is strongly observed from water vapor in the 6.2 micrometer channel, this one here. And lower, warmer layers in the troposphere are more humid, so only signals from the upper atmosphere will reach the satellite in this band. In the 7.2 micrometer channel, the other one, radiation is less absorbed, so radiation from lower levels can also reach the satellite. But neither of the two channels can actually see to the surface, to the Earth's surface. So the higher up there is moist air in the atmosphere, the lower the temperature of this layer is, and the lighter the gray shades of the image are. It's actually more simple. So dark color means dry areas and bright colors means moist areas. We will see some examples now. In this image, there are the weighting functions that show the relative vertical contribution of radiation emitted by atmospheric substances in different infrared channels. And you can see the two water vapor bands dominate the upper and middle troposphere, here 6.2 and 7.3. This radiation intensity is called radiance and is dependent on the amount of water vapor, of course. If there is higher moisture, the absorption is higher and the re-emission is also higher, hence we have a brighter signal. It also depends on the vertical location of the humid layer, of course. If there is low level humidity, it cannot be seen, but the high level humidity can be observed by the two channels. And of course, the temperature of the water vapor, which is also dependent on the vertical location of the humid layers. So this is more or less a little bit the same. Okay, here we have the water vapor image from today 9 UTC. We have already discussed the dark and bright areas a little bit. Now I would like you to mark areas with PV anomalies. Try to keep in mind what the... Okay, I think I have to allow you to make annotations, obviously, or allowed annotates. I think it should work, right? Okay. Okay, someone is already marking PV anomalies. So what I wanted to say was, try to keep in mind what physics are behind PV anomalies a little bit. Okay. Okay, well, yeah, I see you are trying to mark the dark areas. That's a very good approach. It might become a bit more clear. I will now switch the slide. Okay, I think I had to stop annotating before. It might become more clear when we overlay the PV height of 1.5. In this way, we treat the water vapor image a little bit like a 3D surface. And you have already seen, for example, this area here, or here, a small one. Also, this are areas with higher PV. So why do we see the dark areas where we have these higher PV values? I think I have an image here. Yes. So remember the theory of the downward bending tropopause that causes subsidence at one side, and therefore the intrusion of dry stratospheric air here. So this is why dry air comes from the stratosphere down, and the water vapor image appears very dark. Okay, so my personal recipe, however, is to look for a darker spot, like this one over Great Britain, for example, then following the lines from the outside to the center of the rotation, for example, this line, or one more, it doesn't matter, any line that goes into the center of the rotation, and if the curve is cyclonically, I can be sure it's a vorticity maximum. If the curve's anticyclonically into the center of the rotation, that swirl has to be a vorticity minimum. In this case, it's rather difficult to find a vorticity minimum just by finding the curves, or the cyclonic or anticyclonic curves. I would guess that there is maybe one over here, Switzerland, northern Italy, but it's quite difficult. I actually wanted you to have a look or try to estimate where the jet stream is at the moment. I think it's not so easy here in this picture, but if you would like, you can try, and maybe also keep in mind having, okay, I have to again allow to annotate. Okay, so yeah, well, that's very good actually. And maybe also a small hint, try to remember having the vorticity maximum on the left-hand side and the vorticity minimum on the right-hand side of the jet stream. Okay, very nice. Wow, I'm impressed. I will go now to the next slide, where I have overlaid the geopotential lines and the wind barbs, so we can actually see the jet stream over here and also going a little bit here farther eastwards. Very good, thank you. So what does this all mean for the actual weather? I would like to make it a little bit more easy for you and show today's natural color RGB plus the radar plus the geopotential. So we have mostly weak gradients over 1,000 Europe with clear skies, almost no clouds, and more weather action over Northern Europe. Here we have this frontal system with a occlusion over Great Britain, and the cold front that stretches out to the Atlantic, and some other smaller systems here in the east. I also have some webcams here for you. So we see over Wales, we have very windy weather, wet and cloudy. Over Barcelona, there is blue sky and sunshine. In Switzerland, there is also a little bit of sunshine, also a mixture of sun, of clouds, and quite similar in Bergen in Norway, where we have sun and clouds at the moment. Now let me jump back a couple of days to Saturday. Maybe some of you can remember that there was a cold front that was not only nice to observe for us, but also caused quite some damage through hail and flooding. This is a quick overview. This animation shows the lightnings, and it perfectly shows the path of the front, starting with thunderstorms early Saturday in the morning over Germany and lasting till Sunday. Okay, here we have the infrared 10.8 image from Saturday 12 UTC. I show you this because I want to make a comparison with the water vapor image on the next slide. Sorry for that again. While we have quite dense clouds over here, and also sun coming in from the Atlantic, Southern Europe appears rather cloud-free without anything special. Now, looking at the water vapor image, it gives us a very different impression. The atmosphere is full of patterns and structures, and one is especially well pronounced, the dark stripe in the middle here. So what has a little bit looked like a bunch of clouds in the infrared image is now a very nice contrast to the surrounding here, especially at this border. If we make a cross-section through this area, we can identify the cold air coming from the northwest, plus a PV maximum in very high levels. And this is connected with the dry intrusion on the backside of the front, as you can see here in this schematic as a yellow area or arrow. Okay, how can we use all this information in our daily forecast routine? Well, water vapor information is especially important in air mass and convection RGB products. This comes very handy as we are dealing with a convective situation here. So, in combination with different other channels, we can create the convection RGB. This composite provides information about the cloud top height. This is the red channel. It tells us about moisture content in middle and upper layers in the troposphere. Then the cloud top particle size and temperature. So high reflectivity for very cold cloud tops, small ice particles, the green channel, and the blue channel tells us about cloud top phase. So it's information about ice or water clouds. It is very useful for detecting very high cold cloud tops with small ice crystals that appear very bright and yellow. We have here a nice example in the middle of the front over southern Germany and Czech Republic, for example. Okay, let's also have a look how this front has affected the surface. This is the radar signal from August 22nd, from the morning till the evening. We have the front coming in, some single cells already before the front, and then altogether moves over complete Austria, bringing lots of precipitation, lots of hail, maybe not lots, but enough hail. So a very well pronounced cold front. And there were especially two cells bringing hail and a little bit more damage, one in the south of Austria, south of Graz. Here we had crushed trees, flooding, lots of flooding and damage of buildings and so on. Also lots of car accidents. And the second thunderstorm cell that caused lots of damage was actually close to Vienna in Lower Austria, where the main damage was on the wine plants. You see the hail on the floor, on the ground, and the plants are all damaged, and yeah, no wine this year. So also flooding, hail, but luckily the car wash is open. All right, so I will now stop with reporting unpleasant news, and I would like to pass over to Andreas, who has prepared something exotic for us. Thank you very much.
Thank you, Yasmin, for this nice presentation on the thunderstorm. Unfortunately, I do not have nice things to show you because I'm going to speak first. Before the extra topic comes, I will speak about the last 4 days of August that will come now, and the situation will not be that nice. Summer will be over soon. And I have prepared a few NWP charts where you can see a nice trough. That's the front Yasmin already showed. Nice trough over the British Isles, which moves down to Spain. Yasmin has also shown a nice image, webcam image of Barcelona. So for the people there, enjoy the beach because on Saturday it will be over. So the trough really goes down deep to Spain and Morocco, and will move in the next days until end of August to the middle of Europe. So if you are in the eastern part of Europe, you're lucky. You will enjoy the summer weather longer than if you're in the western part. Well, temperature, winter is not here, not yet, but still the temperature is going down. And with the deepening of the trough, the colder temperatures also arrive to Spain. Still, we have very warm temperatures over Northern Africa and also over Turkey. It's still very warm here. And these warm areas will stay at least until end of August. But what is also very interesting is that we have regions here in the north where it's really hot. The temperatures are really, really high, and a few cold spots here, but the picture is completely different from winter or late winter, early spring, where we have a lot of cold air in the north. This is not the case. And I'm just thinking aloud, and I was wondering if this summer has been quite a normal summer. It was not extremely hot, and it was not extremely cold. It was something in between, really a normal summer. And I wonder if this is because the temperature gradient between the north and the south is not that high, because we have, as you see here, quite warm areas towards the North Pole. There's no strong temperature gradient, and maybe this is a reason, but I'm not sure. This is just thinking aloud for this really normal summer this year. So you see that the cold air penetrates to the center of Middle Europe until the 1st of September. And then situation gets a little bit better. It's getting a little bit warmer, but yeah. I don't know if you remember or if you have seen it. It came to the news in Austria on 19th of August. Polarstern, this is the German research vessel. It reached the North Pole. So it came on the water. Now it's summer and it's quite warm, as you have seen. The ice was breaking. But what was really interesting is this is the statement from one of the physicians and meteorologists on board. He said, I translated it into English because he said it in German. Most of the time we were running through open water until we reached 87 degrees 30 north. And then they saw water until the horizon. And only then they were in the ice. And on 19th of August, they reached the pole on the waterway without any big problems. So this is, in my opinion, a clear sign of the relatively mild weather we had this winter and in the previous winters also on the pole. So to continue, what is also interesting to me, I took this chart from the internet, from Wetterzentrale, is the temperature difference from the 30 years mean. And then here you can see, of course, the trough deepening, showing colder than normal temperatures, and still very abnormal warm temperatures here and here in the polar regions. So in fact, it's the same, but more or less climatology chart shows you the warm area still pre-existing until the end of the month in the western, in the eastern part of Europe, while in the western part summer is really over, at least in August. Well, and now for something completely different. I don't know how to come to this topic and how to make a transition. I chose this slide from Monty Python because I jumped now to a completely different topic. And be warned, this will not serve you in any way for your work. It has no relevance and might even not be interesting for you, but it is of extreme beauty. It is a topic of satellite meteorology that shows really nice features. And though I'm working quite a long time now with satellite meteorology, I have discovered that only a few months ago, and I would like to share that with you. What is the topic? What is it about? It's open cell, closed cells, you know that, and in special, I would like to show you the actiniform clouds. And you know what the open and closed cells are. These are shallow convection in a very shallow layer below 2 kilometers. They have often this honeycomb structure, like the bees produce. Either they are open or they are closed, like here. So there are two kinds of them. You do not really recognize them from below. You see stratocumulus clouds. You need cold air over warm sea, and they are rarely observed over land. They do exist over land, but not very often. And what is also interesting is that one would think this region here has more precipitation than the open cells, but there is a study from an American university that it says it's absolutely the contrary. You have more precipitations in the open cell areas below the clouds, of course, and less precipitation, more drizzle-like precipitation in the closed cells. So let's come to the actiniform clouds. So again, here this is open cell and closed cell. Here a schematic from satellite manual that shows you the air circulating, uprising, giving birth to these smaller cells. And this here is the form of the honeycomb. Well, and if you have the closed cells, then the cells are just larger and cover most of the area. So let's come here. Sometimes, I wrote here, we see a more radial structure in the open cells. These are the actiniform clouds. And now I would like to ask you if you can see this more radiant, or it's like the spokes of a wheel. Can you see the structure? I would like you to annotate it. First, I have to know how to... Oh, you can annotate it? Okay, fine. Yes. You see it? Fine. So I think it's not so obvious. You have to have seen some before. But there are structures that look completely different. They do not look like open cells anymore, but they look like spokes of a wheel. And this is nicely recognized here, fine. It's quite difficult. I have some other examples where you can see it better. But first, I have the slide that goes back into history. It was first discovered in 1962. And here you have such an example from a very early meteorological satellite. And this is a very nice example already with this, it's a bit like a snow crystal, but much larger, of course. And it was always recognized as a form which is something in between the open and the closed cell, with some weird things going on, that there's a kind of self-organization that looks like that. But it was not really a topic in literature, nor people really cared about that very much. Only later, when the satellites had a better resolution, like MODIS, then you better saw this structure. And here you have this actiniform clouds in a very nice structure, here and here, also here. Yeah. But sometimes, as you can see here, they take the form of leaves. So you have to have a little bit imagination. I don't know, maybe it's kind of banana leaf, something like that. So you have this radiant structure that appears here, and it's kind of leaf structure. And the beauty of these things is that this happens from alone. There's nothing artificial in that. It just happens. So, and this is the last image from this year, early this year, which really shows you the actiniform clouds at their best. And I think if there's something which is really nice in satellite meteorology, then it's this image. And yeah, it's completely useless. I confess, it's not good for anything, but it's just beautiful. And I wanted to share that with you. So I have a last slide. This is just to remind you the next weather briefing, which will be held by IPMA, the Portuguese Met Institute, and the date is already fixed. It is September the 29th. Yes, this year at 12 UTC at our regular time. So thank you very much, and I hope I could show you something new. And maybe you one or the other day you will find, when satellite resolution is okay, find these structures in the satellite images.